Hello everyone, my name is May. Today I will like a brief of my report about the England and Wales demand forecasting in terms of the courses data science, and we are group 7, which is will be presented by Hoàng Minh, Vũ Văn Đào An, Thế Cương, and Thu Thủy. So for the first one, I will talk about the outline, the table of contents. So the first one we have to do is the background objectives. The second one is data and methodologies. The third one is results and analysis. And the fourth one is conclusion and future work. So for the first part, I will interview you to Trần Thế Cương, who will have a short presentation about the first part.
First, background and objective. First year background, short-term lot of forecasting year core task in a power system operation, data generation, scheduling, reserve planning, and market decision heavily depend on accurate lot expectation. However, with the increasing integration of renewable energy and regional power transfer, net demand has become highly volatile. Consequently, even a small forecasting error can lead to a substantial extra balancing costs and operation risk. Uh, Second is gap and objective. First, a focus on England and Wales. We target the England-Wales demand series because it represents the main consumption hub of a GB system. This region large profile is uniquely shaped by dense population center, working day routines, and a strong temperature sensitivity related to heating. Second, architecture screening and feature quantification. At the preliminary stage, we evaluate three candidate model: random forest, XGBoost, and CNN LSTM. We aim to quantify exactly how much large demand, temporal structure, weather, and a public holiday contribute to the overall forecasting accuracy. Third, operational and practical utility. Our ultimate goal is to identify a suitable forecasting model that is not only highly accurate but also fully interpretable, providing clear feature level explanation for operation no decision support. That concludes the background and objective of our project. Next, I would like to invite my teammate to present part 2, data and methodology.
My name is An, and I will present part 2, data and methodology. In this section, I will explain the data set we used, the research workflow, the machine learning models, and the evaluation matrix. First, the data set. For this project, our target variable is England Wales demand, which represents the electricity demand in England and Wales. The dataset contains around 139,464 hourly observations, confer covering the period from 2009 to 2024. Since this is a short-term load forecasting problem, using hourly data is important because electricity demand changes significantly throughout the day. Besides historical demand data, we also add two external data sources. The first one is weather data, including temperature, humidity, cloud cover, wind speed, and degree day variables. These features are important because electricity demand is strongly affected by weather conditions. For example, low temperatures may increase heating demand, why high temperatures may increase in cooling demand. The second one is calendar and holiday data, including weekends, bank holidays, and the days before and after holidays. These features help the model understand differences in electricity consumption between working days and non-working days. Overall, our dataset combines historical demand, weather information, and calendar effects to better capture real-world demand patterns. Next, we move to the research workflow. Our research workflow follows several main steps. First, we collect data from different sources, including electricity demand, weather data, and holiday data. Second, we perform data pre-processing. In this step, we clean the dataset, handled missing values, converted timestamps into a consistent hourly format, and merge all the data sources based on time. Third, we carry out feature engineering. We create lag features, rolling mean features, time-based features such as hour and day of week, as well as weather and holiday related features. After that, we split the database on time order. Since this is the time series forecasting problem, we do not use random splitting because random splitting may be cause data leakage. Next, we change and compare three candidate models: random forest, XGBoost, and CNN-LSTM. Finally, after the baseline screening stage, we select random forest as the main model. Then we continue with validation, hyper, hyperparameter tuning, and 24-hour demand forecasting. Next, we selected three candidate models because they represent different modeling approach. The first model is random forest. It's backing-based ensemble model. It builds many decision trees using different samples of the data and then average their predictions. The main advantage of random forest are that it can handle nonlinear relationships, reduce variance, and provide feature important source scores. This makes the model easier to interpret. The second model is XGBoost. It is boosting-based model. Unlike random forest, XGBoost builds three sequentials sequentially, where each new tree tries to correct the errors made by the previous trees. XGBoost is usually very powerful for tabular data, but its performance depends heavily on hyperparameter tuning. The third model is CNN-LSTM. This is the deep learning model designed for sequential data. This CNN part extracts local temporal patterns, while the LSTM part captures longer-term dependencies in the time series. However, CNN LSTM is less interpretable and usually requires more computational resources. After comparing the baseline performance of the three models, we select random forest because it achieved the best baseline result and was also more interpretable than the other models. To evaluate model performance, we use four main metrics. The first metric is MAE, or mean absolute error. It measures the average absolute difference between the predicted demands and the actual demand. Since the unit is megawatt, MAE is easy to interpret. The second metric is RMSE, or root mean square error. RMSE gives a higher penalty to large errors, so it is useful for checking whether the model makes serious mistakes at a certain time point. The third metric is MAPE, or mean absolute percentage error. It expresses forecasting error as a percentage, which makes it easier to understand the relative size of the error. The fourth metric is R-square, or coefficient of determination. It shows how much the variation in electricity demand can be explained by the model. The higher R-square means better explanatory power. In addition to these metrics, we also compare the model with NACE baseline, tested the contribution of weather and holiday features, used walk-forward validation from 2022 to 2024, and analyzed the errors under different operating conditions. In the next section, we will discuss the result and analyze how well the final model performs.
So, hello, my name is Ming. So I will now present the detailed result of and the analysis of our forecasting models. So the first one, what do we have here? The hourly and holiday demand patterns, which is the first one. You can see that on the left side is the hourly our demand pattern. So we observe that a clear bimodal day patterns with the morning and the evening peaks. More importantly, on the right chart, which is demonstrates the severe impact of the bank holiday. And as you can see, that is the demand drop significantly, which is you can see here the max gap about 8,500 megawatts as the evening peaks, which is roughly a 21% reduction compared to the normal working day. And this just justifies encoding holiday status independently rather than just using the simple weekend. So on the next slide, we have the correlation and the temperature effect. So let's look to the relationship between the temperature and demand. To show it, we have the U-shaped curve on this is perfectly reflect the physical characteristics of the UK grid. Like the steep rise on the left is driven by intense heating during the harsh winters, with the peaking at 35,600 megawatts as the minus 5 degrees. You can see that on the chart. And on the far right, which is at the from 28 to 30 degrees, we see about the 23,000 megawatts, which is a reduction. But at the end of the 30 degrees, we see a slightly upstick, which is mean like the cooling load from the air conditioning, because this like the relationship is highly non-linear, and the traditional linear regression completely will be failed here. And yeah, so with the next part, we got architecture screening, which is how did we choose the best model for forecasting. Now you can see that we got three models here, which is the random forest. Second one is XGBoost, and the third one is CNN and LSTM. And as clearly be seen that the random forest will achieve the best baseline, which is the MAE, just around 1006, compared to 1057 of the XGBoost and 1060 of the CNN RSTM, and also the R square, which will better than two of the others. So we selected the random forest as like our primary model, not just for its like accuracy, but it also provides the excellent feature. Moving to the next slide, we will compare it into the naive baselines. So why did we do that? Normally in time series forecasting, the hardest model to beat is often the simplest one, which is assuming tomorrow will be exactly like today. So as can you see, our like random forest reduced the MAE by 41.9%, which is compared to the strongest seasonal baselines of the daily life is much better, which is this proves that our model isn't just like lazily repeating yesterday data. It's like actively learning the complex rules of weather and impact of the calendar. So like moving to the feature importance, ranking the first one in this feature importance, we got the rolling mean 24. By far is the strongest predictor, like is representing the fundamental base load in the recent 24 hours. And interestingly, why the individual holiday indicators carry like the modest individual weight, they consistently appear in the top 20 features, and which is make the model more precisely and localize the adjustment during the non-working periods. And for the next part, we got the feature contribution and refinement. Let's see. From the first one, we got here through like our ablation study, we isolated this effect, which is the where the variables provided the largest improvement, like dropping the MAE to 1016. And the combining with holiday data here and the temporal lag control, where we like using like the hyperparameter tuning will brought out our final MAE down to 967 megawatt, which is the data clearly show that the feature engineering contributed like more to the model success than just tuning. So for the next part is the robustness and the error breakdown. As you can see about the two red bars here, which is the bank holidays and the warmest 10% errors. I mean, when we break down some errors by operating the conditions, we see the model is heavily challenged by the abnormally event, which is like bank holidays and the warmest 10% of hours. And additionally, the error naturally grows with the forecast horizon reaching the MAE about 1088 megawatt. And this like indicates that our residual risk is concentrated in rare and extreme operating regimes. And to conclude for all of these data and analysis, I got the final 24-hour forecast and evidence of just one day, which is the 2nd of the January 2024. And you can see that why it tracks all the overly shape perfectly like this. But I want you to see more focusly on this. We got the under forecast nearly up to the 4,000 megawatt, which is extremely dangerous. Like it can lead to the grid instability. This is why other future work proposes using the asymmetric loss function, which is we're punishing the model more severely for the under forecasting like this in the future, and forcing it into the prioritize the grid security. Yeah, I can show it like in here. So the limitations still there. So we'll make to the end of our presentation, which is like the conclusion and the future work we will present by Thủy.
Now, I would like to briefly summarize to the conclusion and future work of our project. After hypermaster tuning, our final random forest model achieved high accuracy. Value as compressed to the strongest daily seasonal net base mass. Our model reduced the MAE by 41.9%, providing its ability to capture complex nonlinear structure beyond simple seasonal replication. K-driver feature analysis indicates that weather is the strongest external driver for demand, while holiday indicators are crucial for adjusting anomalous day loss profiles, robustness, expanding window validation across the test year from 2022 to 2024 demonstrates highly stable performance with the MAE consistently remaining between 920.8 and 954 megawatts. Future works balance optimization. We plan to performance compressive hypermaster tuning with the full feature set for the other two candidates architecture XG Boost and CNN LSTM to ensure a match and rigorous final ranking. Fixed errors mitigation. We aim to introduce quantity loss or asymmetric loss function to actively measure and reduce the symmetrical under forecasting observed during peak hour. Target high risk segment. Future efforts will focus on improving model capability during the high errors green, especially targets spring holiday and external warm weather periods. This conclusion and presentation of Group 7. Thank you thank you very much for your time and attention.